Hello everyone, hope so you are doing good. Myself Heather Kapasi and I will be taking this session on shell energy balance. Moving forward, let's discuss the content of the session. So here we will be discussing shell energy balance in detail, what is this approach and how to apply it in heat transfer problems, and we will be discussing the boundary condition that we must use while solving such type of problems. We will be particularly seeing heat conduction with an electrical heat source. In that we will cover three cases. Case 1 would be that of an electric wire whose surface temperature is given. The second case would be same electrical wire is there, but now the temperature of the surrounding is given. And in the third case, the wire is insulated by any insulator with different thermal conductivity. So it's like composite heat transfer problem. And then we will be performing 2-3 numericals. So let's start with shell energy balance and understanding it. So whenever any heat transfer problem is given, we can solve it by shell energy approach. So in this approach, first we select a slab or element which is also called a shell. And the shell should be normal to the direction of heat conduction. And then we write the following equation. This equation is nothing but conservation of energy. So what this equation states is the rate of energy by convective transport into the system minus rate of energy out by convective transport, that is out of the system. So this term consider the convective transport or the convective form of energy. Then the second two terms consider the molecular transport, that is rate of energy in by molecular transport minus rate of energy out by molecular transport. Then the rate of work on the system by molecular transport minus rate of work done by the system. This is rate on the system, this is work done by the system. So here work done is considered, work done term is considered. Then if there is some external work that is being taken care of by this term, rate of work done by system by external forces, and plus if there is some energy production by the system, then that is also considered, and this should be equal to 0. So this is nothing but the basic form of conservation of energy stated for, like, it is being modified for heat transfer problems. So this is nothing but shell energy equation. So now moving forward, then we would write this equation for the thin slab that we have considered. Then we would make the thickness of the shell or the slab approach to 0, which will give us the differential equation. Then we would integrate it. So after integration, we would have integral constants like C1, C2, C3. So we need to find its value. So how we can find its value? So we need this boundary condition. So in this case, boundary conditions are very important. So the first boundary condition is the temperature may be specified at the surface. Like all in the problem, only this temperature of any surface or temperature at any distance would be given, or any point would be given. So this is the first condition. The second condition is the heat flux normal to the surface when given directly, like how the temperature is given. For some particular cases, heat flux would be given, either it would be 0 or whatever its value that might be given. Now the third boundary condition is at the interface the continuity of temperature and the heat flux normal to the interface are required. Like in the case of composite wall, like this is a composite wall if I draw it. So this is like composite wire, this is K1, this is K2, and on this surface, like whatever flux that is coming out of this first surface and that is going out on the second surface, at the interface that would be equal. Similarly, whatever the temperature is that here T0, so at interface for both of the material, the temperature would be same. So this is nothing but the third boundary condition. Let me erase it. Yeah. So the fourth boundary condition is using like we can find the temperature by using Newton's law of cooling. So now let's discuss the problem. So we will be discussing heat conduction with an electrical heat source. So the case 1 is we are given an electrical wire of circular cross section with radius r is given. So the radius is r, then the electrical conductivity is K, and the current is passing. So the electric current density is given, that is I. Due to this electrical transmission, some heat is generated. The rate of heat production per unit volume is given by this expression. This is the quantity, as they are saying, is the heat source resulting from electrical dissipation. So here directly the surface temperature is given. That makes this problem very easy. So it is given that at surface the temperature is T0. It is maintained anyhow. So yeah, it's very easy. So now let's see its solution. So this is how this electric wire look like. It's one portion of, like, this is the electric wire we can consider of length L, and here its radius we are assuming r equal to 0, and as we move forward here radius equal to capital R. So first we will discuss which coordinate system do we use. So as it seems that cylindrical coordinate would be very efficient, or it could be very beneficial to you, so we'll be using cylindrical coordinates. First we need to decide how t is varying. Is it varying with r, is it varying with theta, or is it varying with z, or is it varying with any two of them, or any three of, or all of them? So let's discuss. So as theta varies from 0 to 2 pi. Okay, so as we move like in this surface, as we move in this small surface, we are moving 0 to 2 pi. So on all these points the temperature is the same, so the temperature is not varying with theta, as it is symmetrical. Temperature is symmetrical with theta. Now this is z. So as we see all this point, the temperature is same in all these points which are marked. The temperature would be same in the it would be same for this, like all these points the temperature would be same. All these points also temperature would be same. So as the end effects are neglected, so the temperature does not vary with z also, as end effects are neglected. Now coming to r, as we move radially outwards, the temperature varies. We can feel that here it might be the maximum temperature. As we move away from it, the temperature here, say the temperature is something like T, here the temperature is T center, and outside the surface temperature is T0, and it will be decreasing. So it is only varying with r. So it justifies that temperature is only function of r. So r, we have established that temperature is only function of r. So now we can assume a shell. So here we are at a distance moving this from center, we are moving a distance r, and we are considering this delta r thickness ka shell. So this point would be r plus delta r. and this point is R. So this is our shell. Our shell will look like a hollow cylinder. So now let us apply the equation of the shell balance equation. So which is given here. So here we are only considering the molecular transport, that heat is only transferred through conduction, because there is no way for convection here, because it's all solid. So this term will cancel out, and there is no work done on the system by molecular transport. So this system will also go, and there is no external work done on the system by any external sources. So this also will go. So we only have this 1, 2 and 3. So we can have rate of energy in by conduction, that is molecular transport, minus rate of energy out by conduction, that is by molecular transport, plus rate of energy production, that is the heat energy that is generating, is equal, it should be equal to 0. So yeah, we would be using this equation. So let's solve the problem. So first let me change the color. Yeah, so rate of energy in by conduction. So in this, we are seeing in this element, so here this energy is coming, here this energy is going out at this surface R. So first so this can be written as Q of R. This is flux at R equal to R, and if we multiply it by the perpendicular area, so the perpendicular area would be this into this whole length. So the perpendicular area would be 2 pi R into L. So this is the rate of energy in by the conduction. Similarly, rate of energy out by conduction, what is happening, conduction, it would be Q R at R equal to R plus del R into 2 pi R plus del R into L. And as it is given, rate of heat generation. So the rate of heat generation is given as by SE into volume. This is per unit volume is given, heat generation per unit volume. So what will the volume of our this shell that we have taken, which I am shading here, yeah, so it would be 2 pi R into L into thickness, that is delta R. So as this is an addition, we can assume this to be almost equal to 2 pi R into L, because we can, delta R is too small. So this is it. So now let us form the equation. So Q R at R equal to R into 2 pi R L minus Q R at R plus del R into 2 pi R L plus SE into 2 pi R L into del R equal to 0. So this is in minus out, and this is heat generation term. So we will divide the whole equation by 2 pi L into del R. So 2 pi L into del R. We are not dividing it by R, because R is changing, so we cannot divide it. Otherwise, if there is R approach 0 and this approach 0, this will become indefinite form. So we are not dividing it by R. So this all will cancel out. 2 pi L, and here 2 pi L del R will cancel. So this equation will look like QR at R minus QR at R plus del R into R whole divided by del R plus SE divide SE R equal to 0. Now we will multiply it by minus 1 on both the sides. So this sign changes to minus 1. Here no effect. So del R plus del R minus QR at R whole divided by del R equal to SE R. It will go this side, so it will come plus. So now we will limit x del R tends to 0. So this will change into a differential equation. This is rho R QR upon rho R would be equal to SER. Now we will integrate it with indefinitely. So there will be some integral constant. So this would be R QR equal to SE R square by 2 plus C1. So this is our equation 1. So we can take R on this side, we can divide the whole equation by R. So SER by 2 plus C1 by R. Now logically think that at R equal to 0, there would be some flux at R equal to 0, which is this line. So there would be some flux coming out. It won't be like when we put R equal to 0 in this equation, QR tends to infinity, but it should be some finite value. It cannot be infinity. Flux cannot be infinity. So by logical boundary condition, we can say that C1 should be 0. So we get the flux profile equation, that is QR is equal to SER by 2. You can say this equation 2. Now we can apply Fourier's law that we studied in heat transfer. What Fourier's law is that QR is equals to minus k dt by gradient of temperature that varies with R. So this is equation 3. We will substitute it here. So minus k dt by dr is equals to SER by 2. So dt by dr is equals to minus SER by 2. Okay, so we will again integrate it indefinitely. So this will give T is equals to SER square by 4k minus plus C2. Okay, so this is our equation 4. So now we can apply the boundary condition that they have given, that at R equals to capital R, the temperature T implies the temperature is T naught. So we can put T naught equals to minus SE capital R square 4k plus C2. So from here, I don't have space, I'm writing here. From here we can get C2 as T naught plus SE R square by 4k. So this is our equation 5. Let me write this. So we can substitute C2, substituting C2 in equation 4. So we get our temperature profile as minus SE small r square upon 4k plus SE capital R square upon 4k plus T naught. So I can have T minus T naught is equals to, I am taking SE upon 4k R square common, so this would be 1 minus R square by R square. So this is our temperature profile. So hence we have find our temperature profile. This will be equation 6. So it is like it is a parabolic temperature profile. So we can draw it like this is the, so it is maximum at r equal to 0. So it would be something like this. Temperature profile at r equal to 0, it is maximum at r equal to r, it is 0. Temperature is T naught, sorry, this equation is 0, so temperature is T naught on both the sides. And we can see the flux profile. Flux profile was, it would be something like it would be 0 at center, because the incoming flux that is coming from this side and flux that is coming from this side, they would cancel out each other, so net flux would be 0, so it would be a linear profile. So this is the flux profile and this is the temperature profile. So here this is the end for case 1. Now coming to case 2. In the second case, it's similar to the first case, but the only catch is that they have given that the surrounding of the wire is maintained at temperature Tr. So now here the surface temperature is not given, only the surrounding temperature is given. So the whole procedure would be same, like we would be taking T, and then we can check for Tz, Tr, T theta, so all this would cancel, so T would be function of Tr, same as above problem that we did, and we will get the same equation. Let me just see what equation I was getting. So this equation would be same till this point, everything would be same. So I am assuming that you understand that, like all this convective term would cancel. This term also would cancel. This will cancel, only this and this would be there. So here QR at R minus QR at R plus del R into 2 pi R L plus SE into 2 pi R L del R equal to 0. This equation would be same. So here again we would be dividing by 2 pi L del R, 2 pi L del R, and then we can limit del R tends to 0, and we would be multiplying with minus sign, so it would be dou QR R upon dou R is equal to SER. Then we would again integrate it. Yeah, so we will again integrate it. So here we can get, let me change the color, it's not visible. So this would be QR R equals to SER square by 2 plus C1. So again we can cancel this, so it would be QR equals to SER by 2 plus C1 by R. So by logical boundary condition, QR is equal to SER by 2. C1 is equals to 0 by logical boundary condition, that is by logical boundary conditions. Again we got QR is this. Now but the catch here is, now we are not given the surface temperature, now we are given T air. So here the temperature is T air. So we, like from this to this, there might be convection, because in this whole wire there is no convection, but as we move from, like heat might be transferring from this to this. So we are assuming that this temperature is T naught. So we can assume that Q at R equals to capital R would be equal to H into H of air. This H of air we are assuming H of air into T naught minus T air. We are assuming that this would be a bit hotter than the T air, so it would come here. So this is we are applying, this is our one condition. So this is what we use Newton's law of cooling. So this is the fourth boundary condition that we used, and we have this one condition. So where I will be using it is, like now I will be using Fourier's law. So using Fourier's law of heat transfer, so minus ka K dt by dr would be equal to SER by 2. So we can again integrate it. K dt is equals to SER square by 4 plus ka C2. So T will be equal to SER square by 4K, and this will be only C2 dash, I can say, divided by K. So yeah, this is our equation number. This is equation 1. This is equation 2. Now I will be using it yeah, here I need to use it. I need to find the relation between this. So I can use QR. So QR at R equal to capital R would be SE capital R by 2. So I will be substituting this in this. This is 1. So this is, let me 2. This would be 3. So now I will be substituting this in equation 1. So SER by 2 is equals to H T naught minus T air. So yeah, so I can find the value of T naught is equals to SE capital R by 2H plus T air. So this is at T at R equal to R, T would be equal to R upon 2H plus TR. So this is our boundary condition. This is equation 4. So this we can apply it here. So SE R upon 2H plus TR is equal to SE R square upon 4K. I think it would be minus, yeah, plus C2. Yeah, so we can find C2 value as STR plus SE R upon 2H minus SE plus, sorry, this is minus already, SE R square by 4K. Sorry, this would be capital R square. So this is our equation 5. Now we can substitute this equation back into the equation of temperature that is here. Let me erase it. So yeah, got the space. So temperature profile will look like minus SE small r square by 4K plus TR plus SE, so I think it was capital R by 2H minus, it was plus, yeah, plus SE capital R square upon 4K. So it is a bit complicated equation, yeah, but this is parabolic. This all is constant only. So T minus TR equal to minus SE R square by 4K plus, I'm telling it as a constant delta, where delta is equals to SE R upon 2H plus SE R square upon 4K. So yeah, this is our final equation, temperature profile for the case when the surrounding temperature is given. So this ends our case 2. So now let's discuss case 3. So in this case, we have a wire whose cross section area varies with radius RW till the wire part, and it is insulated with an insulation material whose radius varies from R equal to RW to R equal to R capital RI. And other thing, heat generation is same, and the temperature of surrounding is given, that is TR. So it is a bit difficult question, but the procedure would be same. So here there will be 4 equation. Here there will be QR of wire, QR of insulation material, TR of wire, and TR of insulation material. So there will be 4 profiles that we'll be finding. So starting considering the shell, it would be same that T, we are considering cylindrical coordinates, so T would be only function of T of R and theta and Z would cancel it because of symmetry and because of end effects. So we can have the same equation as QR of W into R is equals to dou of 2R is equal to SE R. This is equation 1. Dou of QR of insulation would be dou R into R would be 0 because there is no heat generation part of insulation. So these are the 2 equations. We would integrate it. So QR of wire into R would be equal to SE R square by 2 plus C1, and QR of insulator into R would be C2 constant. So by using logical boundary condition, C1 would be 0 because at R equal to 0 there would be some finite flux. So this is the pictorial representation. You can see that from R equal to 0 to R equal to, let's say this is RW, and from RW to RI, this thickness is RI minus RW. So by logical boundary condition, C1 will be equal to 0. So we get the QR of wire profile equation as SE R by 2 because we can divide it by this. So this is equation 1. Now the other equation would be that at we cannot put C2 is 0, QR equals to C2 by R. This we cannot put R equal to 0 because R here starts from RW and it goes to RI. So we need another boundary condition, that is at R equal to RW, QR is equal to QR at insulator. So this, if I explain, at this interface, so whatever flux, this is QR at wire at R equal to RW would be equal to QR of insulator at R equal to RW. So this is the boundary condition, so we will be using that. So we will be substituting QRW equal to SERW by 2 should be equal to C2 upon RW. So we get C2 as SERW square by 2. So this is equation 1, 2, this is 3, so this is equation 4. So we got both equation profile. QR at for wire is equal to SE small r by 2 and QR for insulator is C2 as SERW square by 2R. So these are our equation 5 and 6. Now applying Fourier's law, minus K T W dou by dou R is equal to SE R by 2 and minus K dou T I upon dou R is equal to SE R W square upon 2R. So now we are integrating the both equation. So we will get TW is equal to minus K SE R square by 4 K would be down plus C3, and T I we can get as SERW square by 2 ln of R plus C4. This would be minus KI, and this is KW. So yeah, both the values of the conductivity are different. This is inductivity KI and this is KW. This is wrong. This is higher. So yeah, so now let us find value of C3 and C4. So at using the another boundary condition at R equals to RW, Ti would be equal to Tw. This is very important boundary condition. This is boundary condition, modified boundary condition, or sorry, this is no slip boundary condition that we used in a momentum transfer. This is similar to that. So we will substitute them. So Tw would be minus SERW square by 4KW plus C3, and Ti would be minus SERW square upon 2KI ln of RW plus C4. And so we would equate them as SERW square minus 4KW plus C3 equal to SERW का square 2KI ln of RW plus C4. This is equation, let's say 7. We will just keep it now aside. Now we will use another condition, that is T of air is given. So we need to assume boundary condition using Newton's law of cooling, that Q at QI at R equal to Ri is equals to H air TIB, that is minus T air. So at TIB value is QI SERW square upon SERW square upon 2RI H air plus T air. So this is the Ti at R equals to RW, sorry Ri. So we'll substitute that in equation of Ti. So SERW square upon 2RI H air plus T air equal to minus SERW square upon 2KI ln RW plus C4. So here from that we get C4 equation as SERW upon 2RI H air plus of SERW square upon 2KI ln of RW plus T air. So now let's start with numerical. So in this numerical we are given that there are two large flat plates that are porous, and they are separated by distance b. So the upper plate is kept at y equals to b, and the lower plate is kept at y equal to 0. It is given that cooling gas is passed from the bottom plate, which is cooling the hot plate. So the temperature varies at T. The bottom temperature is T0, and the plate's temperature, that is at y equal to b, has temperature TB. So we are given that, and we need to find the temperature profiles across this distance b or between the plate. So first we will be using Cartesian coordinate system for solving this problem. So we can see that T is only function of y, because temperature is varying only in y direction. As end effects are neglected, and it is a steady state, so velocity of a gas we are assuming as constant. As the velocity of the cooling gas is constant. So we are assuming 3 constants. So this is Cp of the cooling gas, that is the specific heat capacity. We are also considering the K, thermal conductivity of the given plate, and we are also considering rho as the density of the cooling gas. So we have established T is only function of y. So writing shell energy balance equation. So that if we do the analysis, so here the gas is coming in contact with the plate. So this and heat transfer is done through conduction, and this heat transfer, like from here to here, there is convection also taking place, and from here to here, like other conduction is happening. So there are only convection and conduction, and there is no heat generation or any work done term in this numerical. So we will write as Qy. First we will consider the element at y with thickness delta y. So this point would be y plus del y. So this is our shell element. So we would be writing energy balance equation for this element. So Qy at y equals to y into, let's say the length of this plate is L and the width of this plate is W. So the perpendicular area would be W into L minus of Qy at y plus del y into area WL. This is because of conduction. Now heat rate because of convection would be rho Cp into velocity of the gas, which we assume to be constant, into T at y into area, that is W into L. WL into del Y. This is quantity per unit volume, heat rate per unit volume. So we are multiplying by volume minus rho Cp V naught T at Y plus del Y into WL del Y equals to 0. There is no heat generation or anything else. So we are now divide the whole term by WL del Y. So here WL del Y. So all this term will be cancelled out. So we will have, and we are multiplying it with minus 1 also. So we will have rho, and we will limit del Y tends to 0. We are making the thickness approaches 0. So we have del Qy upon del Qy upon rho y plus of rho Cp V naught into dou T upon dou y equals to 0. So this is our differential equation that we got. Now we are applying Fourier's law of heat transfer, that is QR. This will be QR equal to minus K dt by dy. So we are substituting here. So dou to QR. Sorry. So this equation, that is equation 1. So equation this would change to minus K dou to T of double differentiator dou to dou r square plus rho Cp V naught dou T upon dou y equals to 0. So let us differentiate. So let us just divide this whole equation by K dou r square minus rho Cp U naught by K dou T upon dou y equals to 0. So we are assuming rho Cp V naught by K as a constant, say n. It will be easy for us. So it would be d2 T upon dr square minus n into dou T upon dou y equals to 0. So using methods of solving differential equation, we are assuming dou T upon dou r as, say, m. This is nothing but m square minus n, m equals to 0. So we have m minus n equals to 0. So we have to a solution. M is either equals to 0 or m is either equal to n. So let's discuss what is the meaning of doing this. So here, to solve this second order differential equation, we assume that the solution might be of the form e to the power ax, something like that. So we got e to the power mx. So we got m value as m equal to n and m value as m equal to 0. So there are so we write the general solution, the t as e to the power 0 x c1 plus c2 e to the power as nx. So we get the equation which can be the probable c1 plus c2 e to the power nx. So now we have two boundary condition. At x equal to 0, we have temperature T as T1, and at x equals to b, we have temperature T equal to Pv. So on solving, we can get, let's put the equation. So at c1 plus c2 equals to T1, and c1 plus c2 e to the power nb is equals to T2. On solving this, we can get the temperature profile as Ty is equals to T0 plus Tv minus T0 e to the power ny minus 1 upon e to the power nb minus 1. So this is our required temperature profile. On further, like we can further simplify it here. T0 minus T0 upon Tb minus T0 equal to e to the power we can say ny minus 1 upon e to the power nb minus 1. So this is the main temperature profile that you are asking for. Now they have also asked us the conduction flow at the lower plate. So we know Qy is nothing but minus k dt by dy. So we can differentiate this equation and we can get Qy as k minus k Tb minus T0 into n e to the power ny upon e nb minus 1. So we can, as we want the heat flow conduction at lower plate, so we can put y equal to 0 in the above equation. So we can get Qy at n equal to 0 as minus k n Tb minus T0 is upon e to the power nb minus 1. So this is our flux at flux that is passing conduction from lower plate. So this ends our numerical 1. Hope so you understand it. Thank you.